Hello and thanks for joining us. My name is Chris Huxley and I'll be presenting a webinar today titled 2D Model Design Fundamentals, What 2D Mesh Resolution is Necessary. This is a rehash of a presentation that I gave at the 2018 Floodplain Management Association Conference in Reno, Nevada, USA. Let's start with a presentation introduction and overview. I'll be talking about cell size convergence quite a bit today. That's more or less the underlying theme behind the whole webinar. To start with, before I talk through the workflow or the different methodology that we've applied here, let's just define what cell size convergence means. Reading word for word here from the screen, in a well-designed modelling software, cell size convergence refers to the tendency for model results to trend towards a common answer as cell size decreases. If we focus on Mona Lisa here, we'll see that as the resolution is coarse, you're not getting a very good rationalization of the image, but as cell size decreases, she comes into view. When it comes to hydraulic modelling, we see a very similar trend where as we move to smaller cell sizes, we converge to a common answer. Why is this worth talking about? Small cell sizes ultimately result in lots of cells and in turn result in long simulations. A practical model is something that works, which gives accurate results, but also can run within a certain time frame that it doesn't adversely impact a project. So this concept is really important. What will I be talking about today? We've gone and done a suite of scenario tests using two different case studies. The first case study is a rural assessment which looks at dam inundation or dam break flows down a valley. The second scenario is an urban scenario where we've got a densely urbanized lower portion of a catchment, and we're doing scenario testing to define when convergence will occur in both of those situations. Further to that, I'll be doing some comparisons against some industry best practice 2D modelling guidelines, and the image on the right shows you the guideline I'll be comparing against. It's the Australian Rainfall and Runoff Project 15 report, two-dimensional modelling in urban and rural floodplains. If you haven't read this document before and you're new to modelling, I highly recommend downloading it and having a read. It's a very thorough document, stepping through every aspect of 2D flood modelling. You'll find it on Google by searching for Australian Rainfall and Runoff and Project 15. It should be top of the list. Delving straight into that guideline document, and I'm paraphrasing here, but there's in section 10 from memory, there's a single page of the 240 page document which talks about cell size, and it lists 4 factors to be considered when you're creating a model. Factor 1 is the scale of topographic and flow regime. 2, the desired level of output detail. 3, the length of event time and model simulation time. 4, the size of the area of interest. Further to that, there's a table below, which I've also paraphrased here, and it's given some recommendations relating to both the type of modelling but also the situation for which it applies. Starting at the top there, if you're modelling flow in a channel using a 2D scheme, ultimately you should be aiming to have 5 or more grid or mesh elements laterally across the channel. For an urban situation, they recommend a resolution of 6 foot to 15 feet, or in metric units, 2 meters to 5 meters. Flow in a floodplain, it's common to see something which is 30 foot to 100 foot resolution, or in metric 10 meters to 50 meters. And in lakes and estuaries, they actually recommend a flexible mesh approach, because in that model framework, it's much easier to define a range of cell sizes that match the features which influence the hydraulics. This slide here actually reminds me, so this was presented at Reno, which obviously is in America. So it was initially developed using feet as the primary unit. I've added in metric units here so that people both in America and outside America will understand the metrics that we're talking about. Case study number 1. This is the rural example, and I've actually taken this from the Environment Agency benchmark dataset. This was a study that the Environment Agency set up from memory. It was 2012 or 2013. It's an excellent benchmark dataset where they compared different modelling packages for half a dozen different model scenarios. And we'll be focusing on just one of those test cases that they created, and it's known as test case 5. What we have is a valley. At the top of the valley, where we have the red marker here, they've applied a dam breach hydrograph, and that's the image on the top left that you can see. So we have an inflow. It peaks at 3,000 meters cubed per second in US units. That's around 105 cubic feet per second. The model itself was run for 30 hours, even though the breach hydrograph only goes for, say, 100 minutes. The reason they set these constraints is so that different modelling packages could be compared for speed and result on a like-for-like basis. The original Environment Agency models used or set a requirement that the model be defined using a 50-metre resolution. We've taken their model dataset and ran it for a full suite of resolutions. We have 10 metre, 20 metre, 50 metre, 100 metre, 150, 200 and 250. If you look at the figure on the right, you'll see the valley itself is 18 kilometres or 11 miles long, and there's a series of numbers down the channel 1 through 6. For this case study, we've just really focused on reporting location 4 and 5, which are down the bottom of the catchment. What does the flooding look like? Here's just a brief animation to show you the flood behaviour associated with this event. So you can see the water flows from left to right downstream. Excellent. Let's jump in and have a look at the results for this first test case scenario. Before doing that, I'll talk about what we're looking at here first. In the top left, you'll see a presentation of the 2 reporting locations we're focusing on, and overlain on top of that is a grid mesh for the resolution in question. The graph on the top right relates to reporting location 5, and the graph on the bottom left is for reporting location 4. In both cases, we're reporting water level versus time, with water level on the y-axis and time on the x-axis. These graphs here, these results, will be the baseline to which all the other simulations will be compared against to test for convergence. This model here, it was run at 10 metre resolution, so 33 feet, and it ran in 284 seconds. All these simulations were run using TUFLOW HPC and GPU on a GPU card. Stepping through the results, let's see, now we're looking at the 20 metre result. Matches exactly on top of what we previously had for the 10 metre results. That's good convergence. That model ran in 98 seconds. Next, the 50 metre resolution result. Still good convergence. Also a very quick run time, 32 seconds. The 100 metre test case, so 328 feet, we're still seeing convergence. In the top left, you can now see the mesh more showing up more nicely, simply because there's less elements than the finer resolution examples. Moving on to the 150 metre case. Here you can see there are significantly less cells. There's only 840 cells in this model. They're quite coarse relative to the valley, and that coarseness is resulting in a poor result at reporting location number 4. You can see there that we're not picking up the peak water level, and also the receding limb is much lower, or is lower than all the preceding simulations. And as you'd expect, as you move coarser and coarser, the results get worse and worse. Okay, we've observed that the 100 metre resolution result has converged with a result which is consistent with the finer resolutions. Let's now do a comparison between that result and the Australian rainfall runoff guideline document. The first thing I noticed when I looked at these results is that the flow magnitude associated with the dam break means that the hydraulics of this valley, as the flood wave propagates down through it, is more or less acting like an open channel. Now, the recommendation from Australian Rainfall and Runoff was that for open channel, you should have greater than 5 grid elements laterally across the channel. So in this instance, 5 or greater elements across the valley should show convergence, and we're seeing that. So more or less we're getting agreement with the guideline recommendation, which is really nice. One thing to consider here is that the optimum resolution for your project may not exactly match those guideline recommendations. Although we're seeing convergence at 100 meter resolution, depending on the problems that you're trying to solve, you may want to go to a finer resolution than that upper limit. In this instance, because the models ran so quickly, from memory, the 10 meter ran in, was it 5 minutes? I think it was 5 minutes. You could well go with a 10 meter resolution and still have run times that are really quick and easy to deal with. Let's just look at the hydraulics here as to why this resolution is necessary. We need to make sure the resolution of our mesh adequately captures the geometry that we're trying to model. And if you go to less than 5 elements across an open channel, then you really don't pick it up to sufficient resolution. The next thing we want to consider is velocity or flow. One thing to be aware of here is that all 2D solvers, to my knowledge, represent or calculate one velocity per cell face. What that means is if you were to go to a coarser resolution than the 5 grid elements across the open channel or valley in this instance, you really wouldn't be picking up the variation in flow velocity across channel to a fine enough resolution, and that does actually have an impact on your results. Let's go to the next slide here, because it really is a real-world demonstration of how treatment of momentum and inertia associated with that velocity definition comes into play. What you're looking at here is an image taken from the Brisbane River Catchment Flood Study Calibration Report. The yellow dots are recorded peak water marks or flood level debris marks. The red number next to it is the actual value that was surveyed, and the black number is the TUFLOW model result. The yellow number between the two is the difference between them. I'd like to focus on these 2 marks on the Kangaroo Point bend. And what you'll see, or what you'll notice if you look at the values, is that the water surface elevation on the inside of the bend is substantially less than what was recorded on the outside of the bend. It's in excess of 0.5 metre difference between the two. This behaviour is called superelevation, and so we have angular momentum forcing the water around the outside of the bend and pushing the water surface up there, compared to the inside of the bend, that is. If we relate this back to hydraulic modelling, it's really important that you get the velocity distribution or variation of velocity across channel accurately represented within your model. Otherwise, you won't be replicating this behaviour in your results. Here we have test case number 2. This is the urban test case. We have a catchment which ranges in elevation from sea level up to around about 2,000 feet. That's the image on the right. The catchment itself is 21 square miles or 54 square kilometres in size. We're running a 24-hour event using a direct rainfall approach, which applies rainfall to every single 2D cell in the model. We're modelling 2D overland flow. There's also some 1D open channels in there, and also some underground pipe network features. We're doing all this modelling using TUFLOW HPC. This here is a presentation of the land uses that are applied in the model. We have a undeveloped upper catchment and then a densely urbanised lower catchment. Here is a summary of the different cell size models that we've run. We're doing everything, or we've got 6 different models, and they range in size from a 10-foot resolution, so that's 3 meters, with 5.8 million cells, up to a 75-foot or 23 meter resolution case and that model. Let's look at some results. Much like the last test case, for these urban results, we're starting with the finest resolution result first. The image you're seeing on the right there is just a presentation of the water surface elevation results. So you're getting some really nice definition of flow down the streets and also along the catch drains on either side of the street. This model took 9.2 hours to run, and it will be the baseline for which we do our analysis against all the other simulations. Rather than stepping up gradually in result, I'm actually going to work backwards now. So we'll start at the 75-foot resolution model and then trend downwards back to the 10-foot. So you can see how the image on the right will gradually conform to a common answer once we are converging to a common result. You'll see there's a graph on the left down the bottom. Let's just zoom in on that a little bit so I can tell you what that is. It's a histogram of best fit, I guess you'd call it. What we've done is we've subtracted the water surface elevation result from the coarser model from our target, which is the 10-foot resolution model, and summarized those results in a histogram. The center of this graph defines the area of best fit. Okay, here you can see the green bar is assigned a tolerance of plus or minus 0.25 of a foot, yellow is plus or minus 0.5 of a foot. And it trends outwards as you get out towards the edges of the graph. Your result is considered worse. If you're working in SI units, let's just do the conversion so you don't have to on your head. So the green zone is plus or minus 7 centimeters and the yellow zone is plus or minus 15 centimeters. The next data set result, we had the 50-foot example. This is also a pretty poor result. You can see it in the top right. Going down to the 30-foot example, it's getting better, though not great. The model runs really quick, but I probably wouldn't be comfortable using this on a project. Next we have the 20-foot example, and the results are really coming into focus now in the top right. You can see the flow down the roads, and you're also even picking up some deeper channels, or drains along each side of the road, which is really nice. Now this model took 1.8 hours to simulate. This could probably be appropriate for a flood forecasting application. You know, you've got quick simulation times. The result is reasonably good. You're getting 85% agreement with the finer resolution result. So it could be good for flood forecasting. Let's go down to the 15-foot resolution, or 4.5 meters, and here you're seeing good agreement with the 10-foot or 3-meter case. This model takes 4.4 hours to simulate, and we've now got 89% of the result, the cell-by-cell result, with good agreement to that 10-foot resolution case. By comparison, we'll just step back to the 10-foot case. You could see the figure in the top right really didn't change much at all. The one key difference here is the simulation time. We've gone from 4.4 hours up to 9.2. Let's discuss these results a little and also compare them against the Australian Rainfall and Runoff Guideline recommendation. First up, we observed that we observed convergence in this case when the resolution was less than 20 foot, which translates to 6 meters in SI units. And that roughly aligns with what the guideline stated. Fortunately, in this case, the road corridors are so wide that we can adequately get a nice result, slightly larger than what the guideline said. I think its top limit was at a 5 meter resolution. Once again, as per the last test case results, what I would use in an actual modelling scenario or project scenario not only depends on the result convergence, but also how the model results would be used. And I mentioned this slightly when I was presenting the results. The 20-foot result, or maybe even the 30-foot result might be appropriate for flood forecasting situations where you're really focused on getting a quick turnaround in results and a broader assessment of the flood risk. If I was looking at a detailed assessment to design your flood levels for planning purposes, I'd probably go to the smaller resolution, maybe even down to probably even a 12-foot resolution, which is between the 15 and the 10, just so that my simulation turnaround time isn't as excessive as 9 hours. That was the 10-foot resolution, but it would probably come in at around about 6 hours, so something that's reasonable. Once again, let's just put some thought into why such a fine resolution or why this resolution is necessary. And this is quite obvious. In urban areas, you've got lots of obstructions, buildings, fences, and those features obstruct the flow. So it's really important that your mesh is fine enough to adequately represent the change in flood behaviour that those obstructions cause. And that's considering not only the change in flood level, but also the conveyance, that's change in velocity. And you can only achieve that if you have a fine mesh resolution. That concludes our presentation of results and analysis. Let's just close things out with some general discussion. First off, it's really pleasing that the recommendations that were provided in Australian Rainfall Runoff Project 15 were confirmed valid. They rang true. The recommendation in terms of the number of cells across an open channel, which in this instance was a valley, but still the concept is transferable, were true. Similarly, the cell size range that they recommended for urban situations was also confirmed true. One thing that I'd like for people to think about is this question here, actually, and this will more or less lead on to a webinar that we'll post in the not too distant future. The question I'd like to ask is, does mesh convergence guarantee your results are correct? I'll just leave a second there for you to think about it. You'll recall that in all situations that we presented here, as the cell size reduced, the model results converged to a common answer. Now, does that mean that the numbers are right? And the answer is no. And the reason for that is the results that we receive out of our hydraulic models is inherently based on the inputs that we put in. If there's errors in those inputs, albeit accidental errors, they will then translate through the results and mean that the results aren't accurate. The only true way that you can verify, or that you can achieve accurate results with some level of certainty, is to calibrate your models. Calibrate to historic events and compare those results against those historic flood marks or flood gauges. That being said, I'd love to talk about that more here, but that's a big topic in itself. So we'll close out this webinar now and save the calibration talk and discussion for another day. So please tune in when we do publish the calibration webinar. It'll be a really interesting discussion. So we'll save that for another day. Thank you for listening. We'll close out now. If you have any suggestions on future technical webinars, I please encourage you to email support@TUFLOW.com, and we'll try and add it to the list of things that we'll host online as part of a future webinar. Thank you very much.